reflection of light surface, the reflection of light by surfaces. So we looked at a plane mirror, and we also looked at curved mirrors. So there was something we missed out on when we were doing plane mirrors, and that's lateral inversion. So I'll quickly talk about it. Then from there we return to curved mirrors to take it further. So lateral inversion. Lateral inversion. It is the sideways reversal of an object which is given as the image, which is given as the image, or which is seen as the image formed by a plane mirror, formed by a plane mirror. So lateral inversion is one property of plane mirrors. When you put an object in front of the plane mirror, the kind of image it forms is going to be laterally inverted. That is, it is going to be inverted sideways. So it means that left looks right and right looks left. For example, if you stand in front of a mirror, a plane mirror, the one in your house or barber shop, if you raise your left hand in front of the mirror, inside the mirror, that is behind the mirror in physics terms, you are going to see a replica of yourself, an image of yourself. But it will appear as though the person is raising the image, you can see the object. The person in there is raising their right hand instead. And when you raise your right hand in the mirror, it's going to appear as though the person in the mirror is raising their left hand instead. So that phenomenon is what is known as lateral inversion, and it is a property of plane mirrors. So objects produce images that are laterally inverted. So let's take examples. So say we have a plane mirror here. We have a plane mirror here. Quoted on one side and the other side is the reflecting surface. You put an object here, put an object here. This is the object. This is the plane mirror. The kind of image you are going to be getting is going to be laterally inverted. That is, this is facing this side. When it comes here, it's going to be facing this side. Now, and let's explain how we know that and why it is so. Is this. Instead of us having something that looks like this on this other side of the mirror, we have something that is in the opposite, that is laterally inverted. The left side becomes the right side here, the right side becomes the left side. Now, why would it be wrong for us to have something like this instead? Is this. You remember when we were talking about plane mirrors? We said that, or one of the well-known properties of plane mirrors is that the image distance is the same thing as object distance. That is, the distance of the object placed in front of the mirror from the mirror itself is the same thing as the distance of the image formed from the mirror. You understand? Let's show that. You have your mirror here, and you place an object here. The distance from where this object is to where the mirror is, let's call that one x. Now, an image will be formed there. An image will be formed there. The distance from where the image is to where this mirror is, let's call that y. It has been observed, it is always true that x is equal to y. That is, the distance of the object from the mirror is the same thing as the distance of the image from the mirror. Now, if this holds true, this explains why the image formed by this object cannot also be in the same orientation. The reason is this. Look at where the end of the arrow is, the distance from here to where the mirror starts from, to where the mirror is. If you measure that same distance, for this case, if you are picking this case now, if you measure the distance from where this end of the arrow is to this mirror backwards, you can see it's much longer. Then this condition is not satisfied. Do you understand that? So, but if you pick from here to, but if it is this first case now, this one is wrong. But if it is this first case now, the distance from here to here will be comparable, will be the same thing with this. Do you understand? So objects are laterally inverted by plane mirrors. So let's take another example. This is the image, laterally inverted. So let's say you have the letter, the word brown placed in front of a plane mirror. Check out right series and jump. You'll see many questions on them. So, can you take a guess? What letter do you think will have first of all here? It definitely cannot be B because if it is B and it's not going to be in the same orientation like this, you cannot have something like this. But remember that left looks right. This part that is facing here will be on the other side. So that will be something like this. Though this is still wrong. Wrong in the sense that look at the distance of B from where the mirror is to the distance of the image of B to where the mirror is. Does that tally? Is it the same thing as the condition we have here, where the image distance was always equal to the object distance? No. So that would mean B has to be somewhere here instead. So that the distance of the my drawing might not be accurate, might not be to scale. So that the distance from where the image is to the mirror is same thing as the object distance. So n is going to be the first. N is the closest to the mirror here. The same thing happens in the image also. And it's going to be reversed sideways. One trick you can always use is when you are taking an exam or your answer or your question paper, just turn it the other way. You understand? Just turn it around. The image you can see is what the plane mirror is going to give you. Just turn it around. Let's say this is your paper and you have brown. You are asked to write out the type of image you are going to get from the plane mirror. Just turn it the other way. The new thing you can see on the other side is what you are going to get. So for this end is going to turn this way. So we have something like this. We have something like this. Yeah, we have something like this. This one comes here. Yeah, this one comes here and the other place. Sorry, it's a bit like this. This one comes here instead. Then things like W, O, M, A, what again, I. The change for this ones, the change is not, it's like you can't change that because should you say they are symmetric or kind of like, no single change will happen because like O now, even if you switch the orientation multiple times, it's still the same thing. So W, O, then R will become like this, and B becomes like this. Interestingly enough, if this were to be the original object, if you bring it here, the image you get will spell brown. You understand? So that makes sense. Let's return to computers. So let's return to computers now. So our focus will be on concave mirror. So I'll start with the concave mirror. We have the concave mirror whose outer part is the non-reflecting surface. The outer part is coated concave mirror. So this is just a cross section. It has some parts. This point here is called P, somewhere here is called F, and somewhere here is called C. We soon see what those points or regions mean. Now, you remember in the last video that was posted that we drew a sphere of which this cross section of the mirror is just a part of. So I'm going to redraw that. So this is the full mirror now. This is the full mirror. We only cut out this part. You understand? To get this. So this is the full part of the mirror. The center of this mirror is C. Yeah. And this is T here. Somewhere here is F. Oh yeah, yeah. The outer part is still rotated. So now let's explain what each of them mean. P is the pole, and this is pole P, and it is the center or middle of the mirror itself. The center or middle of the mirror. The center or middle of the mirror. The center or middle of this mirror is called the pole. Let's talk about F, focus. focus capital F. This is the point on the principal axis, or let's talk about principal axis first, so that focus will not seem strange to us. Let's talk about principal axis. Principal axis, PC. This line PC, principal axis, PC, principal axis, PC. PC is an imaginary line drawn from the pole P to the center of curvature. C is known as the center of curvature. To the center of curvature. So objects usually stand on it, and images also have their part standing on it. So this imaginary line that is drawn, it can produce for the backwards here behind the mirror. So this line that goes from P to C is called the principal axis. It is imaginary line that is drawn from the pole to the center of curvature. So let's talk about the focus now. Focus capital F. This is it's also known as focal point. Focal point. The point on the mirror from where rays appear to diverge, it depends on the type of mirror, appear to diverge, or on where they appear to converge. So it's called the focal point. That's where rays will converge. It's a converging mirror. It's on where they will converge, the wash fields, or from where they will diverge. If it's a diverging mirror, they'll spread apart. So what else? Let's talk about the focal length. The focal length, small letter f, small f. So the focal length, this is the distance between P and F. The distance between P and F is known as the focal length. Yes, the distance between P and F from here to here is known as the focal length. Interestingly, PF, the length PF is actually equal to the length FC also. They are equidistant. So from P to F is the same thing as from F to C. So the distance between P and F, or loosely translated between F and C. So let's look at center of curvature. Center of curvature C. So this is the center or middle. Looks like this, but it's slightly different. This is the center or middle of the sphere. Now, of this whole sphere. Now, the middle of the sphere. You know, for example, a circle has a center, right? So the center of this sphere also, the center of this sphere from which this mirror is cut out, the center of it is what is called the center of curvature. Why the center of this mirror itself that was cut out from it is the curve. This is the center or middle of the sphere, of which the mirror is just a part. Of which the mirror is a part. So center of curvature is C. There's one more thing. Radius of curvature. Radius of curvature. Radius of curvature. Usually taken as small letter R. This is the radius of curvature. Radius of curvature is the distance from P to C. The length, the magnitude of the distance of that line. The line itself that joins P to C is the principal axis, but the magnitude of that line, the length of that line, is the radius of curvature. The length of the line PC, length of the line PC. So the magnitude of the distance between P and C, between pole and the center of curvature is known as the radius of curvature. Now there's a relationship between the focal length and radius of curvature that we can even see. Remember that from P to C is R. Let's show it to you. From P to C is R. But we said that from P to F is small letter F, is focal length. The same thing as from F to C. That would mean that F is equal to R over C, right? So F F equals to R over 2, that is, focal length is equal to the radius of curvature divided by 2. Now, let's come to ray diagrams. Ray diagrams for concave mirrors. For concave mirrors. So, there are three rules to be used when you want to draw ray diagrams for concave mirrors, depending on where the object is placed. So, you need any two of them to construct ray diagrams. So, let's say the three rules. Number one, any ray parallel to the principal axis. We know what the principal axis is now. Any ray parallel to the principal axis. To PC, let's use notations. Any ray parallel to, okay, let's write it. To the principal axis. Any ray parallel to the principal axis returns, that is reflected, through the focus F. So let's show what that means. This is your mirror. This is P. This is F. This is C. What this one is saying is that if there is any ray coming from the source or from the object and is parallel to this principal axis, it's parallel to this principal axis, any ray coming like this, when it gets reflected, it must pass through F. So it will go this way. So this is the reflected ray, this is the incident ray. This is what we want to see. Rule 2 says that any ray that passes through the focus, any ray that passes through F, through the focus, through F, must return, that is, must be reflected, parallel to the principal axis. Must be reflected parallel to the principal axis. So let's see what this also means. We have your mirror this way. This is the pole, this is the focus, and this is the center of curvature. So any ray that passes through F, let's say a ray comes from somewhere here and passes through F to meet the mirror. So it must get reflected in the direction that is parallel to this principal axis. It must go all the way through like this. Is that what? So, and rule 3 is that any ray that passes through F, that passes through C, any ray that passes through C must return along that same path, must return through C. So this one is not going to indicate that it's going to pass through that same C, must return through C. And this is what we have. We have this, we have this. So you have P here, you have F here, and you have C here. So if the ray comes from C and hits the mirror this way, it is incidental on the mirror. It's also going to return through that exact straight line this way. So this is the so we need any two of them to construct ray diagram. So let's take them. Let's apply them now. So depending on the positions of the object. So there are 5 positions that we can have for the object. So we'll take for 5 cases for object position. So we want to see what's going to happen to the image. 5 cases for object position. So case 1 is that the object, when the object is between P and F, that is, when the object is somewhere in between P and F, what type of image will form? Another one is when the object is at F or when it's on F, when the object is exactly on F. Number 3 is when the object is between F and C, when the object is between the focal point and the center of curvature, when it's in between somewhere here. And number 4 is when the object is at C When the object is at the center of point, when it is here, what type of image is going to be formed? Then the last one is when the object is at 12, or sorry, this is also the same thing as when it is at 12. And this one is when the object is beyond C. That is between C and infinity. So when the object is between C and infinity, that is what goes on. If the object is somewhere between C, this is not straight. If the object is between C and infinity, it is beyond C, what are the images going to be formed? So let's start from the very first one. Number one is object between P and F. So I have my mirror, the concave mirror. This is P, this is F. When you are doing this on your own, when you are practicing, please make sure you use your ruler so that you have accurate results. And make sure that the distance from P to F is set as F to C. You understand? So that you get accurate results. So I'm going to place my object between P and F now. My object is somewhere here now. Now, we have to apply two of any of these rules. At least two of any of these rules to each of them. So, if we check rule one here, any ray parallel to the principal axis, I think that one applies. We can get a ray from this object, light rays coming. We can get it through this object. It's going to use the mirror here, and it's pass through S, pass through F after reflection. That one works. Let's say the second one works. Any ray that passes through F must return parallel to the principal axis. Looking at this, we can see that the ray cannot pass through F because it's already before F. Even if it manages to pass through it here, there is no mirror here. Yes, on this is where the mirror is. So, only when it's pass through is if it was somewhere here, you understand, the ray can pass through F. But it's here already, so that means we discarded rule 2. Then we are only left with 1 and 3 because we have to use at least rules. Any ray that passes through C must return through C. Definitely, the ray can go from C and meet this object here and be inserted on the mirror, then it will return back in that same direction. So let's do just that. So remember, this is my object. It's between P and F. So this is the incident ray. It gets reflected, but it passes through F. Passes through F. The next thing now is that a ray must go from C now to meet this and come all the way here. Sorry, and I need to withdraw this somewhere because of the type of image I'm going to get. And I think I should get the pattern. So, give me a few seconds to get a ruler. Okay. So, let's start again with object, case 1, object between P and F. So, we have a mirror something here. The outer part is coated. Remember, we are still discussing concave mirrors. Then, I want to draw the principal axis, the line of the principal axis. You can always reduce this backward because some of them will leave us image somewhere behind the mirror. So, this is the pole. Somewhere here as the focus and somewhere here as the center. Ensure that they are equidistant. The distance from here to here, the same as from here to here. So the object is between P and F. I have something like this. So a ray coming will hit the mirror here, along here, and it's get reflected through the focus. So I'll do just that. So this is the incident ray coming from the object. Then it will pass through the focus this way. So it gets reflected. Make sure you produce this as long as possible. So the next thing now is a ray will also come because we saw it that only the first and the A ray can go from C, pass through this, and hit the mirror. Let's see what happens. So this goes this way. Remember, it's also going to get reflected along that same line. Now, what do you notice? Now, there is something. How do we know where the image will form this? Where the reflected rays intersect. You understand? So it does not appear as though they are going to be intersected along here because you can see that the gap in between the two reflected ray for this one is along this line, and reflected ray for the first incident ray is along here. The gap in between them is getting wider. That is, they are not converging anywhere. So that means they are converging somewhere. So we have to produce this line forward. So I'll produce this one back for brother. That's behind the mirror now. So I've done this now. I'll produce this one also until the meet. Because it appears they will converge somewhere behind the mirror. You do see that? So the next somewhere where the meet is where the image is going to be. And wherever the meet is where the edge of this image is going to be. So let's write what the properties of this image is. Image number one, it is virtual. You remember what we mean by virtual? The image is found behind the mirror. Remember, this coated surface is the back of the mirror. So the image is behind the mirror. It is virtual. A virtual image is an image behind the mirror. I cannot cast on the screen. If any of the images in the case were somewhere here in front of the mirror, we say it is real. So it is virtual. Number one, it is virtual. The next thing is that it is erect, that is, it is not upside down, it is not inverted. It is erect or upright, the same thing. It is erect or upright. Now, how about the size? Is it reduced or magnified? It is magnified. It is not diminished. It is magnified. It has become bigger. And what's the position? It is behind the mirror. That's the location. It is behind the mirror. If it were to be formed somewhere here, we would say it's between F and C, but it's located behind the mirror. So it is behind the mirror. Let's see for case two. So I have M here, which is a pole. I have F here, and there is C somewhere here. So the new case now is object is at F, object is at F. So when the object is at F, like it's exactly on F now, let's see what happens in this case. In this case, remember rule one, ray parallel to PC, rule two, ray passing through F, ray passing through F, and the third one, ray passing through F, and the last one is ray passing through C, ray passing through C. If you check there, there is no way that can pass through it again because the object is already on there. So the first one, the ray can travel parallel to the principal address. So that's the incident ray for this. then it will get reflected along the focus. So we have this. Then another thing that can happen is for it to pass through C. The ray will come from C and pass through the mirror like this. This should be a bit closer. So I'm trying to make sure that we have the same distances. So what do you notice about this image, even if about the radar diagram for this, even if it is poorly drawn, is that the two reflected rays are parallel to each other, yes or no? So they are not going to intersect, they are not going to be intersecting anytime soon. So the image formed is at infinity. If they ever meet, we might not be so sure what is going to happen, maybe magnified or real or virtual or something. But it's at infinity, somewhere parallel. That's in the ever meet, no parallel is not. So